Welcome to this explainer. Today, we're diving into the incredible Cinderella story of Sericin, a literal biological underdog. We're looking at some fascinating research from the Journal of Functional Biomaterials that totally flips the script on one of our most ancient industries, silk production. We're going to explore how a protein treated like absolute garbage for decades is now leading the charge in cutting-edge medicine, cosmetics, and sustainable engineering. It really poses a staggering question, right? For centuries, the global silk industry prized only one thing, those smooth, shiny threads. The rest of the cocoon? It was chemically destroyed, systematically stripped, and literally washed down the drain as industrial waste. We're talking millions of gallons of wastewater loaded with this secondary protein just tossed out. But now, modern science is asking, wait, did we actually throw away the best part?
Section 1. The misunderstood glue, fibroin versus sericin. Let's look at exactly what we've been throwing out and why.
To understand the waste, you kind of have to look at how silk is actually built. Silk from the Bombyx mori silkworm is basically two main proteins. On one hand, making up about 70 to 75% is fibroin. That's the famous fibrous core, the thread itself that's been used in textiles and biomedicine forever. On the other hand, making up the remaining 25 to 30% is sericin. This is a globular protein that acts like an adhesive gum, literally just holding those fibroin strands together. And for the longest time, the industry wanted absolutely nothing to do with this glue.
And honestly, a highly cited quote from a 2003 scientific paper perfectly captures this stigma. They basically claim that sericin was the major cause of adverse immune responses and hypersensitivity. This single, totally misguided idea branded sericin as toxic waste and, no joke, set research back for years. The general consensus was just keep the fiber in, destroy the sericin.
But thankfully, the scientific community woke up. Once researchers actually bothered isolating and testing pure sericin, they realized those old assumptions were completely wrong. The publication trend over the last decade shows an absolute explosion of interest. Papers on sericin went from barely a trickle in the early 2000s to a massive spike, hitting over 400 papers a year by 2023. Science finally realized they weren't dealing with toxic waste. They had stumbled onto an untapped gold mine.
Which brings us to Section 2, inside the silkworm, and how this glue is actually made.
So the silkworm's silk gland is this highly specialized biological machine divided into three distinct parts. Starting in the posterior silk gland, that famous fibroin is secreted. But as that fibroin travels forward, it hits the middle silk gland, and this middle section is entirely dedicated to synthesizing and coating the fibroin with three different layers of our underdog protein, sericin, right before it gets spun out of the head.
If we zoom in closer to the tissue level, we can actually see the exact microscopic factories where this intricate protein is built in the cytoplasm before being secreted. What's wild here is its chemical makeup. Sericin absolutely loves water, it's highly hydrophilic, and it's packed with 18 different amino acids. The standout here is serine, which actually gives the protein its name and equips it with some incredible chemical properties we'll get into in just a minute.
But here's where the biology gets super cool. Inside the silkworm, sericin is soluble, and its molecular structure is just a bunch of loose random coils. But the second it's secreted into the outside world, it reacts to the temperature and humidity. The protein literally shifts its structure, transforming from those loose coils into rigid formations, known as beta sheets. This phase shift is exactly what causes the glue to dry, locking the fibers together to form that tough protective cocoon.
All right, Section 3, the extraction challenge, detaching the glue. If this stuff is so amazing, why is it so hard to get?
Well, the problem has always been how we extract it, a process called degumming. For centuries, separating the glue meant boiling the cocoons in harsh soaps, acids, or intense alkaline solutions. Sure, that perfectly cleaned the valuable fibrin thread, but it completely obliterated the delicate molecular structure of the sericin, turning it into this degraded, unusable soup. Plus, this conventional method created tons of toxic wastewater. Even early biological or thermal methods usually just left you with heavily degraded, low-quality sericin. But today, sericin is getting a major modern glow-up. To actually use this protein, researchers had to figure out how to detach it without ruining it. Enter innovative techniques like infrared radiation heating, microwaves, and supercritical CO2. These modern methods safely tease the protein away from the thread without harsh chemicals. Best of all, they preserve sericin's high molecular weight and structural integrity, while completely cutting out that toxic chemical runoff.
Moving to Section 4, purifying the protein. From extract to powder. Once it's detached, how do we get pure, usable sericin?
It's basically a rigorous four-step journey. Step 1 is that degumming extraction we just talked about, leaving us with a raw liquid. Step 2 is precipitation, and filtration to separate the sericin from any leftover fibroin or impurities. Step 3 is dialysis to neutralize and remove any residual chemicals. And finally, Step 4 is spray drying or lyophilization. This sucks out all the water, turning that purified liquid into a highly stable, incredibly versatile powder ready for the real world.
And that leads perfectly into Section 5, Medical and Cosmetic Marvels, Sericin's Superpowers. This is the real climax of this explainer.
Because of that unique 18 amino acid profile we mentioned earlier, Sericin has an absolute arsenal of superpowers. First off, totally debunking those early 2000s rumors, it is highly biocompatible and naturally biodegradable. But it gets better. It's naturally anti-inflammatory, it has antibacterial properties thanks to the amino acid cysteine, high levels of serine and threonine make it a potent antioxidant that fights aging, and get this, arginine and alanine actually bind to tyrosine, turning it into a powerful agent for UV defense and skin protection.
And this web of applications is Sericin's ultimate triumph. Because of these biological superpowers, this former industrial waste is now a premium, star ingredient across multiple industries. We're talking regenerated biomaterials turned into hydrogels for advanced wound healing and tissue engineering. It binds so well to charged molecules that it's being used for targeted drug delivery. In cosmetics, it's starring in high-end anti-aging creams. They're even using it to make biodegradable food packaging. The turnaround is just incredible.
It is a true scientific redemption story. A protein that was literally discarded and labeled toxic for decades has proven to be one of the most versatile biomaterials on Earth. And it really makes you wonder, as we push for more sustainable manufacturing, if we completely misjudged a simple silkworm's glue for that long, what other industrial waste materials are out there, hiding in plain sight, just waiting to change the world? Thanks for joining me on this explainer, and keep questioning what we throw away.